Hi everyone, I'm going to show you how to do some of the problems in the class notes so that if you're using these for practice problems you can check your work. So this is slide 70 in the notes. It's in the free fall section. A coin is dropped from the top of a roller coaster and the height of the ride is 110 meters and you're asked to find the time it takes for the coin to hit the ground. So for free fall problems I like to draw a picture and kind of map out what I know. So if this is the roller coaster, we have a coin at the top here and it's being thrown downward. It's going to fall a distance or a displacement, so delta y of negative 110 meters. So if we're dealing with acceleration, we have to pay attention to what direction the object's moving in, so downward is considered negative. So our displacement is negative 110 meters. We also know that this coin is only being affected by the acceleration of gravity. So our acceleration is going to be little g, which is a constant. It's always negative 9.8 meters per second squared. And then we need to find the time it takes for the coin to hit the ground. So since we're dealing with acceleration, there's two equations we could use that have acceleration in them. So there was A equals VF minus VI over T, and there was delta X equals VIT plus 1/2 A T squared. So we have to figure out which one of these we're going to use. Since we're looking at a free fall problem specifically, a couple things would change with these problems. A, the acceleration that we're dealing with is gravity. So A actually becomes little g. And then with displacement, since we're talking about things going up and down and not left and right, we use a delta y instead of a delta x. So same two equations, we just changed around a few of the variables, but they represent the same thing. So in this case, we want to use this guy since we're given displacement. So our equation we use is delta y equals VIT plus 1/2 g t squared. So I know delta y and I know g. I'm looking for time. So VI I must know as well. So it says a coin is dropped. Dropped is kind of like a hidden variable. When you see that word, it means that there's no initial velocity. So in this case, VI is 0, and this whole term cancels out. 0 times anything is 0. So I'm going to plug in my variables, but first I need to rearrange to solve for t. So we divide out the 1/2 g, and then take the square root. So delta y is going to be equal to the square root, t is going to be equal to the square root of delta y divided by 1/2 g. Now I can plug in my variables. T equals the square root of negative 110 divided by 1/2 times negative 9.8. So plug that into the calculator. Half of 9.8 is 4.9, so 110 divided by 4.9. The negatives cancel, I get 22.4, and then we take the square root of that, and we get about 4.7 seconds to hit the ground. So then part B, the next question with the same problem, is find the velocity of the coin when it hits the ground. So we want to find out what VF is. We knew VI was 0 when it was dropped, so we need to find what the velocity is when it hits the ground, just before it hits the ground. Obviously when it hits the ground, once it's on the ground, the velocity is 0 again. So we want to find just that middle a second before it hits the ground. So for this one, I'm going to use this equation since it has VF in it. So G equals VF minus VI over T. And I know T, I just solved it here in the last problem. To rearrange to solve for VF, it's going to be VF equals VI plus GT. All right, so VF equals VI is still 0 plus G, which is negative 9.8. Don't forget the negative signs when you use gravity, times the 4.7 we solved for up there. So negative 9.8 times 4.7 is a negative 46.06. So we'll say negative 46.1 meters per second. And I know it's meters per second because I'm using G, which is a constant that we use in meters per second squared. So that means the velocities are going to be in meters per second. All right, that was slide number 70.